We're diving into some really fascinating research today. Pure intellectual curiosity driving us towards a potential leap in quantum tech.
Yes, we're looking at a key paper on quantum networking. It's titled Parallelized Telecom Quantum Networking with a Ytterbium-171 Atom Array. Quite a mouthful, but important stuff.
Right, from researchers like Lintao Li, Shi Hu, Jacob Covey, and several others. And our goal here really is to unpack how these ytterbium atoms are tackling the big hurdles, long-distance communication, and crucially, speed through parallelization.
Exactly. How do we build quantum networks that are actually scalable and fast? This paper offers some compelling answers using Ytterbium-171.
Okay, so let's jump in. The first big problem, distance. Most quantum bits, these emitters people use now, they work with visible light, right, or near UV.
That's the common approach, yes. But the issue is, standard optical fibers, the ones that carry our internet data, they lose a lot of that kind of light very quickly.
So you can't just send it down the line. You need
What?
some kind of conversion process.
Precisely. You need frequency conversion to shift that light into the telecom band, where fiber loss is minimal. But that conversion, it's complex, it adds noise, it loses efficiency, it's a major bottleneck.
Ah, okay. So how does ytterbium fit in? What's the solution here?
Well, this is where it gets clever. Ytterbium-171 atoms, they're already known quantities, foundational for top-tier atomic clocks and some quantum processors.
Okay.
But the researchers here focused on the atom's nuclear spin as the quantum bit, the qubit.
The nuclear spin, why is that significant?
Nuclear spins are incredibly well isolated from environmental noise compared to, say, electron spins. This means they can hold their quantum state for much longer, better coherence time.
Longer coherence. Okay, got it.
And the critical part.
Yeah.
They managed to entangle this superstable nuclear spin with a photon that is directly generated at 1389 nanometers.
1389 nanometer. That sounds specific. Is that the telecom band?
Bang on. It's right in that sweet spot, the O-band or near it, where optical fiber loss plummets. We're talking around 0.3 decibels per kilometer. Minimal loss.
So they skip the conversion step entirely, just generate the light directly where it needs to be.
Exactly. No complex conversion hardware, no added noise, no efficiency loss from that step. It's a much cleaner, more direct pathway for long-distance quantum communication.
And does it work well? What about the quality, the fidelity?
That's the other impressive part. They demonstrated entanglement with an atom measurement-corrected Bell state fidelity of narrow 0.950 with a small uncertainty.
0.95. That's really high, isn't it? Especially for the telecom band.
It is. It matches the best results achieved for any atom-like emitter generating photons directly in the telecom band. It really validates this ytterbium approach.
Okay, so that tackles the distance and the noise problem associated with it. But you mentioned speed earlier. For quantum computing networks, entanglement needs to happen fast, right?
Absolutely. If you're trying to link up distributed quantum computers, waiting ages for entanglement links to form just won't work. The key strategy is parallelization, doing many things at once.
Makes sense. How did they achieve that here?
They used a one-dimensional array of these ytterbium atoms. Think of them lined up. And they coupled this array to a matching array of lensed optical fibers.
So multiple atoms talking to multiple fibers simultaneously?
Precisely. Spatial multiplexing. This allows them to attempt entanglement generation across several channels all at the same time. If you have n channels, you get roughly an n-fold speedup in your remote entanglement rate.
An n-fold boost. But that sounds significant. Did it affect the quality? Any interference?
Remarkably, no. They showed the fidelity was uniformly high across these parallel channels, and the crosstalk, the interference between them, was negligible.
Okay, wow. So faster entanglement, same high quality. That's huge for scaling. But there's another piece, right? Protecting the qubits already doing work. MCN.
Yes, mid-circuit networking, or MCN. This is crucial if you want to connect quantum modules while they're actually running a computation. You can't afford to have the networking process mess up the qubits holding valuable data.
Right. You need to connect things on the fly without disturbing the ongoing calculation. How do you isolate them?
They demonstrated they could protect memory qubits, the ones holding the computational state, while performing networking operations on separate communication qubits within the same array.
How? What's the trick?
They use a technique they call shielding. It involves applying a local light shift using light at that same 1389 nanometer wavelength, but targeted only at the memory qubits.
Ah, so using the telecom light not just for communication, but also for protection, like a localized force field.
Sort of, yeah. This light shift effectively makes the memory qubits insensitive or decoupled from the stray light, and operations like optical pumping needed for the communication qubits nearby. It isolates them temporarily.
That's quite elegant, using the same tool for both connection and protection.
It's a critical piece of engineering needed to actually integrate these powerful neutral atom processors into larger functional quantum networks.
So putting it all together, we have direct teletom wavelength generation using stable nuclear spins, high fidelity, parallel entanglement for speed, and MCN capability to protect ongoing computations. That feels like a complete package.
It really does tie together several key requirements. And remember, Ytterbium is already central to state-of-the-art optical clocks. This opens doors to connecting processors and ultra-precise clocks over long distances.
This deep dive was brought to you by embersilk.com. Embersilk is the answer for all your AI education and integration needs. So thinking ahead, if we can link quantum processors and these incredibly precise optical clocks across networks with this kind of fidelity and efficiency, what's the next frontier? Does this open up possibilities beyond just communication or computation?
Well, that's a really exciting question, isn't it? You could start thinking about using the quantum network itself as a distributed sensor.
A sensor? How so?
Imagine using networks of entangled clocks or processors spread over large distances to perform distributed quantum sensing. Maybe sensing tiny variations in gravity, or searching for exotic physics like dark matter fields that might subtly interact with these atoms.
So the network becomes the instrument, detecting things across potentially global scales. That's a mind-bending prospect.
It shifts the perspective entirely, doesn't it? From just sending quantum information to actively probing the universe with the network. Definitely something to watch.
Absolutely. Well, if you found this useful and want more deep dives like this, please do hit subscribe and maybe leave us a 5-star review. It genuinely helps us keep doing this. Thanks for joining us today.